Good morning and welcome to the special webinar session at the 4th International Conference on Nuclear Photonics. This session is part of the conference's general scientific outreach to bring a topic of broad interest to a broad audience. The session is on inertial confinement fusion as we quest for energy sources that provide low carbon output. Often the short list includes nuclear fission and nuclear fusion. With nuclear fission being an intermediate source of energy and nuclear fusion being a long-term goal. Today we have two speakers who will speak on one technique for harnessing nuclear fusion. Our first speaker is Dr. Riccardo Betti. Dr. Betti is professor of mechanical engineering and professor of physics and astronomy at the University of Rochester. He is the chief scientist of the Laboratory for Laser Energetics at the University of Rochester. He's held many leadership positions, including serving as the chair of the Division of Plasma Physics of the American Physical Society, and vice chair of the Fusion Energy Science Advisory Committee. He is a member of the board of Physics and Astronomy for the National Academy, has received numerous awards. This includes the Edward Teller Medal from the American Nuclear Society, the E.O. Lawrence Award from the U.S. Department of Energy. He has co-authored more than 100 peer-reviewed articles. Today he'll talk to us on progress in laser direct drive inertial confinement fusion. Dr. Betti.
Thank you. So this is a large effort. So it's from the Laboratory for Laser Energetics, but includes also other institutions like the Massachusetts Institute of Technology and General Atomics for the targets. So this audience is probably not familiar with all the details of laser fusion, so I'm going to give you a short introduction. Both direct drive and indirect drive aim to achieve the condition for thermonuclear ignition and propagating burn by compressing a capsule to very high density and temperatures. Ignition starts from the center of the capsule, the imploded capsule, which is hot and dense, and then it propagates outward, and that's the propagating burn. In both cases, direct and indirect drive, the goal is to achieve the condition for ignition of a central plasma, which is hot, several kiloelectron volts, a relatively low density, tenths of gram per cc. This is a DT plasma, and then surrounded by a dense, colder plasma that is a reservoir of fuel, and which is hundreds of gram per cc. In general, so the fusion plasmas that works with deuterium and tritium really relies on the alpha particles coming from the D plus T reactions to self-heat the plasma. That is called alpha heating or self-heating. And when that is dominant, that's when you get an enhancement of the properties of the plasma in terms of fusion properties. So the alpha heating is instrumental to achieve ignition of the DT plasma. So you can view a fusion plasma as a blob of plasma, and what goes into the plasma is heating, so energy from the alphas that deposit their energy into the fusion plasma. And then there is external energy that is inputted to the plasma in different forms. In the case of ICF, the external energy is really PDV work, which is compression work from a spherical imploding piston, which is driven by the laser. So a key a key metric is the Q alpha, which is the energy of the alphas divided by the external input of energy. So when the alphas are dominating the external input, so then it's called a burning plasma. When the alphas are much greater than the external input, then you can get an ignited plasma. So there are different stages towards the path to ignition. First, there will be a burning plasma, and then it will be an ignited plasma, depending on the amount of alpha heating that you get. So driving ICF targets with laser is a very inefficient process. So I hope that's clear to everybody. Direct drive is better than indirect drive in terms of coupling energy to the capsule. So when you shine the laser on the capsule, most of the laser energy gets absorbed in this bladed plasma around the capsule, and very little of it ends up in kinetic energy of the imploding spherical piston, which is the energy that you need to ignite the plasma when the spherical piston slows down and stagnates in the center. Just to give you an idea, if you think about an indirect drive, a capsule that is driven by 2 megajoules of laser energy ends up with only about 20 to 30 kilojoules of kinetic energy, which is the one that you need to ignite a capsule. And so the total efficiency, 1.5%. In direct drive, where you shine the laser directly on the capsule, then you end up with roughly 80 to 100 kilojoules of kinetic energy from 2 megajoules of laser energy. That's a 4 to 5% efficiency. So again, it's a small fraction that ends up as kinetic energy from the laser energy, and it's significantly more in direct drive than indirect drive. That gives, indirect drive, that's the importance of indirect drive, the ability to drive more fuel, bigger capsule, and therefore getting more fusion energy gains eventually if it is ignited over indirect drive. So depending on the design, direct drive implosions are degraded by hydrodynamic instabilities and laser plasma instabilities. To name a few, there are so-called Rayleigh-Taylor instability. That's the instability that is seeded by imperfections both in the laser and in the target. Spherical implosions are hydrodynamically unstable, so every imperfection will grow first exponentially in time and then quadratically roughly in time. And the most important seeding of the instability in laser direct drive is the fact that if you take a cross-section of the laser beam, it's not uniform. And that seeds perturbation on the surface. That's called laser imprinting. Then there are laser plasma instabilities, like the two-plasmon decay instability, the simulated Raman scattering, which takes place by the laser interaction in the corona plasma. And that accelerates electrons, which these energetic electrons can deposit their energy while the capsule is imploding, heating it up before it stagnates, increasing its entropy and therefore reducing the compression. There is also another important instability that's called cross-beam energy transfer, where rays in the laser beam that are refracted and intersect rays from another incoming beam take energy out of the incoming beam out of the absorption region. So that's a net, loss of laser energy absorption. The hydrostability metrics that are used in ICF are the adiabat, which is a measure of the entropy. It's defined as the pressure over the Fermi pressure, but it's roughly P over rho to the 5/3, if you think about classical fluid. The higher the adiabat, the higher the entropy, and therefore the lowest is the compression. On the other hand, the higher the adiabat, the more stable is the implosion. In-flight aspect ratio is radius over thickness. The higher the in-flight aspect ratio, so the thinner is the target, the more unstable it is. So those are all stability metrics. And the adiabat, which is the most important stability metric, is set by the strength of the first shock that you drive into the capsule when you turn the laser on. So when you design an implosion, you design the target itself, which has, in the case of direct drive, is a shell of plastic, a CD, and a cryogenic DT ice layer. Roughly on omega, the whole thing is roughly 1 millimeter in diameter. And the laser pulse shapes is a complicated shape of the laser power versus time, where you have a picket in the laser where you send the first shock into the target that sets the adiabat, the entropy, and therefore determine both the 1D compression as well as the stability. And then you have a foot that launches another shock, and then you have a ramp to higher power, and then eventually to full power. So low adiabat is good for 1D convergence and compression. However, high adiabat is good for 3D stability. So it's a compromise between stability and one-dimensional compression. So the target specification and the laser pulse shapes are the knobs that we can turn for optimizing implosions. So we measure many things in an implosion. So we measure neutron yields on omega between different Lyson sites. The neutron yields depends on the fusion reactivity, the density in the hotspot, the volume of the hotspot, and the duration of the burn. You can write the density as pressure over temperature. And so if you measure the temperature like we do through the NTOF, the width of the NTOF signal, and then the volume through the X-ray images and the burn duration through the Newton temporal diagnostic, then this is an equation that you use to infer the pressure that you get when the core is stagnating. We measure areal density, another critical parameter. The areal density is just the integral rho dr of the compressed core. So density times size of the car, and the areal density is measured either from the downscattered primaries of the DT reactions or the backscattered of the anti-edge. So there are different measurements we have along different lines of sight. So a major goal of LLA is to produce scaled ignition conditions on the Omega laser for direct drive. The most important figure of merit is the so-called normalized Lawson parameter, which is NT tau, density, temperature, and confinement time, normalized by the value required for ignition. That can be expressed in terms of areal densities of the compressed core, density times size, the number of fusion reactions that we measure by measuring neutrons, and the mass of DT, which we can infer from the measurements. So then once we do an experiment on Omega, we ask ourselves, Omega is only a 30 kilojoule laser. What we would be getting if instead of using a 30 kilojoule laser, we would be using a bigger laser like the NIF laser. So we hydrodynamically scale the implosion to larger energy and larger sizes. The scaling of the Lawson parameter is straightforward. It's pressure times confinement time. The confinement time scales like size over velocity of the implosion. So therefore, if you get the same pressure and the same velocity, then it scales only like size. So the Lawson parameter scales like size. And if you go to a bigger laser where and you try to get the same condition as you would get on Omega, but on larger sizes, then you have to scale the laser energy with the volume, which is R cube, and therefore the size scales like energy to the 1/3. So either equivalent ignition condition, therefore, requires that the value of chi, which is the Lawson parameter, that scales like size and therefore like energy to the 1/3. When you do an experiment on Omega, you measure chi on Omega, and then you scale it up to megajoule energy, assuming that you have a bigger laser. And if that's larger than 1, then you can say you have reached hydroscaled ignition. If it is larger than 0.8 instead of 1, that's the condition for the burning plasma, not an ignited plasma. The ignited plasma requires chi to be 1. So typically, when you design an implosion, you use one-dimensional simulations because those you can run many of those, so you can make a lot of changes and you can design an implosion. However, one-dimensional simulations are not really accurate to guide the design towards the optimum. So the input, the initial condition on the input conditions are the target specs, the dimensions of the target, and the materials, and the laser pulse shape. Then you run this through the simulations. But then when you do an experiment, and this is a measurement of the fusion yield in terms of neutrons versus the simulated yield, you can see that this is the y = x line. You can see that the simulation do a poor job in reproducing the experiments. Therefore, 1D simulations are not really a good tool to design an implosion. If you can use 2D simulations, the agreement gets a little better, but not a lot better, and they take a lot longer to run. So what we have done at Rochester, we have developed a predictive model that is that marries the the data and the simulations. So it's a statistical model for which you take the implosions, so for which you have the target specs and the laser pulse shapes. You run the simulations, and then you train a model which is on the experiments, which are 300 plus omega implosions in the last 7 years for cryogenic implosions. And then you train this model to correct the simulations. And at the end, you get a model that is pretty predictive. This is the measure yield, and this is now the predicted yield, and this is the y=x line. So now we have a statistical model that is trained on the data, corrects the simulations, and therefore we can use that to design implosions. So the complication of designing implosions is that when you do experiments, there are a lot of things that affect experiments, not just the one I just mentioned, like the hydrodynamic instability seeded by laser imprinting, the laser plasma instability, like cross-beam energy transfer into plasmon decay. There are illumination no uniformities just from the port geometry of the omega laser, 60 beams. This is a hard sphere projection of the illumination. There are the fact that the target vibrates or the laser is mispointed. And so we have things like the so-called L=1 mode, for which the laser is pointed not at the center of the target. And it causes a poor compression of the core and a shift of the core, so a bulk flow velocity in the compressed core, which we can though assess by measuring the ion temperature with the N-TOFs, which so-called apparent ion temperature, which is going to be different whether you measure it along the axis of the shift or perpendicular to it. So by measuring different values of the ion temperature, we can tell how much of this shift is occurring. Other things is the age of the DT field. We fill the target with DT, we shoot it several days later, depending how long between fill and shot time leads to different degradations. So if you wait 2 weeks, you have large degradation. If you have 3 days, you have smaller degradation. And this degradation is due to the helium-3 accumulations. And is we can calculate that, but what we calculate is not really what we actually see in the experiments. So this is all can be though accounted for using these statistical predictions on the data itself. So this led to variations in the design of the targets and the design of the laser pulse shapes. Since we use statistical predictions, the target got bigger. It started with a target with the outer radius of 430 microns. Now I end up with a target of roughly 10% bigger, 470. A ice layer that is thinner from 50 micron to 42 microns. And the laser pulse shapes is very different. As you can see, we started with the laser pulse shapes in red, with a lower picket, a very long pulse shape. And then we ended up with a much shorter pulse shape, so with a stronger picket, and with an average intensity that is even higher. So this is again because with this statistical technique of designing, we are able to use data to optimize the balance between stability and compression. So, and also we were able to extract the dependence on the helium-3 accumulation, which is the age of the fill. And we end up now in the high-performance implosions to be done with a short 3-day fill. Instead, in the old times, it was 2 weeks long. So we also were able to fix the effect of the so-called L=1 mode coming from laser mispointing on target vibration by using a technique based on nuclear measurements of the shift in the N-TOF peaks along different line of sight. This is a case where we have a larger L=1 in the illumination. You can see that there is an L=1 here. This is a hard sphere projection of the illumination. That led to a core that is highly distorted, as you can see here, with a large flow that was measured for nuclear measurements. And a poor DT yield, that's the fusion yield that are here, these shots. Then we were able to infer from the flow measurements what is the correction in the positioning of the target to compensate for the L=1 in the laser. And this compensation led to a higher fusion yield, as you can see, and a rounder core and a lower flow measurement. So now we routinely use the offset in the target the beginning of the shot day to position the target to compensate for the mode 1 in the laser. Recently, we also improved the energetics of the implosions by using silicon doping of the ablator. So in the old times, we used just a shell of CD. Now is a bilayer shell. The inner layer is a CD, and the outer layer is CD doped, CH doped with 6% silicon. So adding silicon led to a larger laser absorption. You can see here the comparison of the laser absorption. This is the laser pulse in the dashed curve, and then the two curves appear as the laser absorption fraction for the undoped case and the doped case. And you can see the doped is higher absorption. As a bonus, adding silicon also reduces the laser plasma stability, the two plasmon decay in particular. We can infer that by measuring hard X-rays. Those are coming from the energetic electrons accelerated by the two plasmon decay instability. This is again is a comparison of the undoped case of the hard X-ray from the undoped case and the doped case. You can see that there is a strong reduction in hard X-ray, so less hard electrons produced with the silicon doping. Now, what are the performance metrics for mega implosions so far after all these design changes? Adding silicon, using offsets, pre-imposed offsets to mitigate the mode 1. So this is what we got. So the neutron yield has been steadily increasing since we used the statistical predictions. The neutron yield has been steadily increasing. We started with 5 × 10⁻³ number of fusion reactions, and we reached up to 3 × 10⁻⁴ in 2022. So a significant increase. These very high yield shots, though, have lower areal densities, so less compression. Therefore, we took a step back and tried to increase the compression. So the yields, the optimum yields actually are around 2 × 10⁻⁴. And those have been achieved with silicon doping. When we look at the normalized Lawson parameter, which is the fundamental metrics that define progress towards ignition, the omega implosions have a normalized chi of 0.2. That's the actual implosion on omega. And the hotspot pressures that it's in excess of 80 gigabars. So we started with roughly 50 gigabars, and now we are up to over 80 gigabars. And we are hoping to get to 100. This one shot seems to be close to 100 gigabars. And we're going to try to repeat that. So this is only one shot. So until we repeat that, we are not sure. So that would be a milestone for us to achieve 100 gigabars of pressure. For omega implosions, if you look at the fusion energy produced in an omega implosion, so you compare that with the energy of the fusing plasma, which is the hotspot, the internal energy of the fusing plasma, it's in the order of hundreds of joules in an omega implosions, and so is the fusion energy. And there are several shots for which the fusion energy is larger than the energy of the fusing plasma. So we call that hotspot gain, fusion energy larger than the energy of the plasma itself. And so omega, for the first time, we see that omega implosions have achieved a hotspot fuel gain exceeding 1. Now, what if we take these omega implosions, the best performing ones, and then we extrapolate that to 2.1 megajoules on NIF? So we can now do the extrapolation. So what we do, we take an omega implosions, we try to reproduce all the observable with the codes. So the codes are tweaked in order to reproduce what we measure. But at the end, the codes reproduce exactly what we measure if you tweak them enough. And then you take that code and just you make the target bigger. So that means you're going to larger energy because that's a bigger target requires larger energy. So if you take those omega implosion results and you extrapolate them to an energy of 2.1 megajoules of laser energy, then what you will get in terms of extrapolated fusion yield, at the best, you will get about 1.5 megajoules. So that's not a gain larger than 1, and it's not ignition. It's in the burning plasma regime. But it is a very good results, and we hope to get above the line very soon. So we're still not matching the Livermore results, which is over 3 megajoules of fusion energy output at 2.1 megajoules. but you know, we are getting there slowly. So there are upcoming experiments that are exciting. So we are going to extend the optimizations of omega implosions at smaller scale. So instead of using nominal scale, which is a laser beam of 150 micron diameter and a capsule of roughly 930 micron diameter, we are going to go to smaller diameter beams, 650, and a smaller capsule. That we call it 80% scale, 0.8 scale. The reason for that is that enables us to access higher intensities on the target. Because now we are the power is maxed out, so we have to reduce the target size, you know, if we want to increase the intensity. So when we look at the laser intensity versus time, nominal shots nowadays are in blue. With the reduced target size, we are able to exceed to reach 1.5 10 to the 15 watt per centimeter square intensities. So that enables us to look at higher ablation pressures and hopefully get higher extrapolated loss on parameters. The other thing that we're going to be trying soon is what is called shock augmented ignition designs. This is something that was proposed by Robbie Scott. It's a variation of the so-called shock ignition scheme. We are going to use the smaller face plates, the smaller beams on omega, to reach intensity of over 1.5 10 to the 15th. The pulse shape is going to look like this. We are going to relax the pulse shapes and then drive a very strong shock at the end. The very strong shock is calculated to collide with a rebound shock. That's the pressure in red at the time of assembly of the hotspot, where the rebound shock coming from the hot plasma in the center collides with a shock launched by this power spike at the end of the pulse, and that should lead to better performance. So we're looking forward to these experiments coming up next year. Now, ultimately, to get the much better implosions, we think ultra broadband lasers is the way to go. The laser bandwidth is critical for both hydrodynamic instability and laser plasma instabilities. And we calculate these are simulations that indicate a much better performance if you can increase the laser bandwidth. So this is the effect of laser bandwidth on laser plasma instabilities. First, on the so-called cross-beam energy transfer. This shows how the laser absorption increases with the laser bandwidth. Those are calculations. So if we increase the bandwidth, we get rid of cross-beam energy transfer. Therefore, the laser absorption would increase significantly. We'll go from roughly 55% to almost 90%. That's a huge increase in laser absorption. Now, when you increase the laser, so by reducing CBET, then you increase the laser energy reaching quadricritical density, and that's where laser plasma instabilities like TPD and SRS take place, SRS even below that. So this is shows how the fraction of other electrons would be the fraction of other electrons produced by TPD and SRS as a function of bandwidth of the laser. If you mitigate CBET, so then you're going to have more laser intensity reaching quadricritical, so you're going to have more laser plasma instabilities of the type TPD and SRS, as in red. However, if you have enough bandwidth, you can kill all these laser plasma instabilities. And therefore, you end up with CBET mitigations or better energetics and no laser plasma instabilities with sufficient bandwidth. So what about the hydrodynamic instabilities? Even now on omega, that has a very limited bandwidth, about 300 gigahertz, you will get a much better beam quality with 300 gigahertz of bandwidth, SSD bandwidth, than without it, as you can see here in the far field spatial laser intensity profiles. Here is the plot of the sigma RMS of the laser intensity as a function of the bandwidth at current omega levels, which is very little bandwidth relative to what I showed you before in those plots. Now, if you increase the bandwidth, you can see that the sigma RMS decreases significantly. So we did experiments to this extent to look at the effect of bandwidth on omega we operate at full bandwidth, which is 300 gigahertz. So the only thing we can do make things worse. So we lower the bandwidth on omega and see how implosion performs. So the stable implosions at high area bat at the alpha equal 5 are roughly insensitive to bandwidth. This is the performance in terms of yield and aerial densities. And you can see that they're pretty much flat as you lower the bandwidth of the laser. And you can see that, therefore, we say that close to full bandwidth, there is really no improvement here going to higher bandwidth for hydrodynamic instability. However, if we go to lower area bat, so more unstable implosions, so they will perform much better in one dimension, so if they were stable, you can see that instead there is a finite slope even at full bandwidth, indicating that if you increase the bandwidth even more, you will get better performance, more yield, and more aerial density. So we expect that higher laser bandwidth will enable performing area bat implosions that are highly convergent, highly performing, unfortunately are unstable with current bandwidth. So, and ultimately, this is a slide of the upcoming test on the new architecture of the laser. We call it FLUX, fourth generation laser for ultra broadband experiments. This will be commissioned next year and will demonstrate for the first time high bandwidth in the laser. So the bandwidth is obtained using collinear OPA. That is used to amplify the broad bandwidth. And there is also demonstration has been done on frequency conversion to the UV, keeping the bandwidth at 13 terahertz. So John Zugel, who is the head of the laser division, will be here, I think, later this week. So he is the architect together with Christophe Dorer of this architecture. So if you have any question on the laser architecture, please ask John. And the FLUX laser will be operational next year, and we will do LPI experiments to demonstrate indeed that laser plasma instabilities are eliminated at bandwidths of 10 terahertz or higher. So in conclusions, implosion experiments on omega have achieved record loss on parameters for direct drive and core conditions that scale to a burning plasma and if energies. We use a data-driven predictive models to design implosions that has been very effective in improving implosion performance. The loss on parameter has been improved by increasing coupled energy with larger silicon dope targets and thinner ice layers. And when hydrodynamically scaled to 2.1 megajoules of symmetric illumination, the omega implosions are expected to be in the burning plasma regime with a fusion yield of about 1.5 megajoules. And the next generation of broadband lasers are expected to improve energy coupling by mitigating laser plasma instabilities and reducing the seeds for hydrodynamic instabilities. That's all I have. Thank you.
So my question is about the cross-beam energy transfer. So naively, I would imagine that it's in general it's much less pronounced in direct drive versus indirect drive, just because of the geometry of the beams. And are the mitigation techniques similar in the direct drive scheme than those of the indirect drive?
Now, actually, it's the direct drive uses cross-beam energy transfer in their favor to transfer energy from one cone to another cone, from the outer beam to the inner beams. So for them, it actually is a plus. For us, is a minus, definitely. So we have a lot of beam crossing, ray crossing. I would say beam crossing, but ray crossing. And the rays are the refracted rays that intersect the center of an incoming beam are very effective in taking the energy out. So we lose, as I said, from 90% absorption, cross-beam energy transfer brings the absorption down to 55, 60%. So it's a big loss, about 50%.
What are the mitigation techniques?
It's bandwidth. So right now, So adding silicon, so there is another mitigation technique that is straightforward to implement, which is making the target a lot bigger than the beam. So in that case, you reduce refraction, and therefore you reduce the intersection of the rays. The problem with that, as you make the target bigger with respect to the beam, right there, then this illumination pattern becomes stronger and stronger and stronger. So therefore, you are seeding an instability, an hydrodynamic instability, because now this is a much larger intensity excursion on the capsule when the beam is small with respect to the size of the capsule, because you are reducing the overlap of the beams. So therefore, then you pay the price. So we can calculate that. That's actually one of the reasons why the optimum target is so far is bigger than it used to be, because we increased the target size with respect to the beam size. Now the beam is smaller than the target. That reduces cross-beam energy transfer, improves the energetics. It makes the stability worse. However, it's a compromise, and this is the optimum compromise so far.
So in this normalized Lawson criteria that you're taking, is there an inherent assumption that all of the plasma instabilities are scaling and are constant from one scale to the next?
Right. So this is something obviously very important that needs to be kept in mind. So when you hydrodynamically scale, you are assuming that there are no new phenomena taking place as you scaled up. Instabilities are phenomena that are threshold phenomena. So if you pass a threshold, you have an instability. Below the threshold, you don't. So for instance, when we scale from omega to NIF, SRS is not an issue on omega, but it's a big issue on NIF scale. So there is no way to account for that other than doing experiments on NIF scale. So LLE has a campaign on NIF to do LPI on NIF scale, because LPI, again, those are instabilities that you either have them or you don't. So they don't scale hydrodynamically. And so we have, there is a recent paper by LLE, Solodov et al. And Rosenberg et al. That shows that despite all of that, it looks like that the hot electron preheat, which is a byproduct of laser plasma instabilities leading to degradation or implosions, scaled approximately hydrodynamically between omega and NIF. It shouldn't in general, but the amount of degradation that you get at NIF scale seems to be approximately the same that you get at omega scale, even though the omega scale is 2 plasmon decay, while a NIF scale is stimulated Raman scattering.
Next speaker is Dr. Benjamin Bachmann. He is a physicist at Lawrence Livermore National Laboratory and is leader of the Hotspot Reconstruction and Diffusion Mixed Group at the National Ignition Facility at Livermore. Today he'll talk to us about the National Ignition Facility Nuclear Fusion Breakthrough.
Thank you.
Sure why it's taking so long to open. There it goes.
There you go.
Right. Okay.
Okay. Thank you very much. Okay. All right. Yeah, to start, I would like to thank the organizers for inviting me to give this keynote talk on behalf of Lawrence Livermore National Laboratory and the Inertial Confinement Fusion team at the National Ignition Facility. The nuclear fusion breakthrough I will talk to you about today has been made possible by the hard work of generations of scientists and engineers who've dedicated their careers to the pursuit of laboratory fusion ignition. And so to acknowledge that, I'd like to start by stepping back for a minute and let you watch a short movie summarizing how we got here. It's okay. All right. Sound was definitely worth it. Okay, so on December 5th, 2022, the National Ignition Facility demonstrated fusion ignition in the laboratory for the first time. And on this shot, the NIF delivered 2.05 megajoule of laser energy to the target to create a plasma with a temperature of 130 million degrees that produced 3.15 megajoule of fusion energy. Now, this shot met the 1997 US No worries. Okay, so this accomplishment has been, again, built on decades of hard work by many people at Livermore in partnership with the whole fusion, plasma, and high energy density science community. And with that, we are now laying the groundwork for inertial fusion energy that has generated a lot of interest by the general population. Although this will require target gains of at least 20 to 100 times or more, this is the first step. Now, the NIF is the world's most energetic laser, enabling the study of extreme conditions for high energy density science. It's 192 laser beams, can output 2 megajoule of laser energy and 500 terawatt peak power. And with that, we can create plasmas in excess of, with temperatures in excess of 100 million Kelvin. That's more than 5 times hotter than the center of the sun. Pressures higher than 100 billion atmospheres and densities of more than 500 grams per cubic centimeter. That's more than 50 times the density of lead. And all of that in less than 10 billionths of a second. Now, the NIF is not only the largest and most energetic laser in the world, it's also the most diagnosed high energy density science facility with hundreds of diagnostics probing the extreme states of matter that are created at the center of the 10-meter diameter target chamber. And the condition generated here can be found nowhere else on Earth. So typically, the NIF delivers about 400 shots in a year, and these experiments probe everything from fundamental properties of materials to radiation transport, and we also perform focused experiments to address high energy density science issues. A core mission of the NIF, however, is to achieve fusion ignition through inertial confinement. So what is that, inertial confinement fusion? Well, fusion is a process that powers the sun and the stars, and it is not easy because we need to squeeze together positively charged particles, overcoming their natural repulsion to fuse them and create a new element. And on the NIF, we use deuterium and tritium to do that, which are isotopes of hydrogen, which when combined produce helium and a neutron, liberating 17.6 mega electron volt, or about 3 picojoule of energy for each fusion reaction. Now, let me put this into perspective for you. If converted 100% efficiently, a single gram of DT fuel could supply an average US household for 10 years. Now, just imagine how abundant hydrogen is on our planet and how much energy is stored in that reservoir. So how are we going to make this happen? Well, inertial confinement fusion can be achieved using high power lasers to drive a spherical implosion. And the way this works is we start with laser produced X-rays that rapidly heat the surface of a capsule containing the DT fuel. Then the blow of plasma accelerates the DT fuel inwards like in a rocket. The fuel eventually stagnates, creating a hot central core, which is surrounded by a dense confining shell. And the core ignites and fusion burn propagates into the dense shell, yielding many times the input energy. Now on the NIF, we are using laser-driven X-ray cavities, which we call hohlraums, to compress the fuel to achieve the conditions for ignitions. So we start with our 192 laser beams, focusing them into the hohlraum. This then creates an X-ray drive with a peak radiation temperature of 300 electron volts. The X-rays ablate the capsule surface, and the capsule starts accelerating inwards, reaching a peak velocity of 400 kilometers per second. Then the fuel stagnates at about 200 gigabar and 500 grams per cubic centimeter. And the central hotspot ignites. Then fusion burn spreads rapidly through the compressed fuel, and in the case of our December 5th experiment, yielding 1.5 times the input energy, or 3.15 megajoule of fusion energy. Now, let me put this 3.15 megajoule fusion energy into perspective for you. So going back all the way to the left here, we start with about 300 megajoule of electrical energy that's provided by the capacitor banks that pump the flash lamps, which then amplify the laser. And with that, we get initially a red infrared laser light of about 3 megajoule. Now we convert that to blue light as it's more ideal for the absorption by the target. But in that process, we lose a whole megajoule. And so eventually we end up coupling 2 megajoule to the hohlraum. And of those 2 megajoules coupled to the hohlraum, only about 250 kilojoule are actually absorbed by the capsule. And of those 250 kilojoule absorbed by the capsule, only about 20 kilojoule are actually given to the DT fuel. And on December 5th, those 20 kilojoule created a fusion energy output of just above 3 megajoule. Now, the key challenge is doing this just right. It's a little bit like trying to compress a basketball to the size of a pea while keeping it as near spherical as possible. Whereas in our case, we have a 2 millimeter diameter capsule that we are compressing to the size of a human hair, where imperfections in the laser drive or the target can lead to fuel jetting out on one side, or mixing parts of the capsule into the fuel, polluting the implosion and preventing the hotspot from reaching fusion conditions. So how do you make a cylindrical oven cause a spherical implosion? Well, first we arrange the laser beam spots on the inside wall of the hohlraum to give us an as uniform radiation field as possible. But that only gets us so far and results in the poles of the capsule being heated more than the waste. And we also just can't increase the power in the inner beams, though, because we are already running the laser flat out. So to balance the radiation field around the capsule more uniformly, we are employing a little trick, and that is by introducing a small wavelength offset between the inner and outer beams. And in the presence of the background helium gas in the hohlraum, then stimulated Brillouin scattering transfers up to 50% of the power between the inner and outer beams. So by fine-tuning the beam pointing and the wavelength difference between the inner and outer beams, we get very precise control over the symmetry, which, if we get it right, leads to a spherical implosion. All right, so this has been a journey of more than 6 decades. It all started with John Knuckles, who proposed the first inertial confinement fusion concept in the late 1950s, but he didn't actually have the means, the effective means to compress the fuel with adequate precision. And then with the invention of the laser in 1960, we got the tool to compress the fuel. And in 1972, he published the seminal paper describing inertial confinement fusion. And since then, we've been building an ever bigger series of lasers to enable experimental access to these extreme conditions. And along the way, that has actually created a whole new field in science called high energy density science, or HED, that has led to many new discoveries and high impact publications. So with that, you see that reaching ignition really is the culmination of decades of passion, hard work, and learning. Okay, so I'd like to play another short movie now, showing you what an experiment on the NIF looks like. And we start again with this aerial view of the NIF building, which is the size of 3 football fields. Then we go into the control room, which is modeled after those used by the NASA and the space program. And there are many operators controlling the key components of each experiment. For example, all the 192 laser beams and diagnostics have to be precisely aligned as we prepare for the shot. Now here, the capacitor banks are charged in under a minute to store this 300 megajoule of electrical energy. And the laser is then born at the picojoule level, precisely shaped in the master oscillator room, which you see here. And that single pulse is then split 48 ways and sent into the preamplifier module, where it is amplified up 10 billion times to the 10 joule level. Here, each of the 48 beams are split 4 ways, making a total of 192 beams that then travel into the main amplifier, where they bounce 4 times and are amplified another 10,000 times. Now, by this time, each beam is about 40 by 40 centimeters and has an energy of 20 kilojoule. The beams then move into the switch yard, which you can see here, that reorients them and makes them arrive at the target center at the same time. As the beams enter the target chamber, they are converted from red to blue light. And here you can see them entering the hohlraum through hohlraum windows. And they are absorbed by the wall, which heats up, generating X-rays that flood the cavity and starts compression of the fuel. And then our wide array of diagnostics record the results of the experiment that are then sent back to the control room and archived for later analysis. All right, so I hope you enjoyed this little virtual NIF tour. And now that you know all about how a NIF shot works, we are almost ready to talk about the details of the recent experiments. But first, we'll briefly review the epochs of NIF target design that led to ignition by plotting the target gain here on the left, which is the fusion yield divided by the input laser energy. Now, in the last decade, more than 800 experiments were conducted that led to an increase in target gain of more than 1,000 times end fusion ignition. So it has been quite a journey. Our first experiments in 2011 were using plastic ablator capsules that had large losses from laser plasma instabilities, leading to poor symmetry, and they were simply too unstable and delivered only 2.5 kilojoule of fusion yield. Then, in 2013, we made the implosion more stable by raising the power in the foot of the pulse in a series of experiments called the high foot campaign. Here, we were basically doing what Riccardo was explaining earlier. We were trading reduced compression with increased stability. But even though we were able to improve the performance up to 25 kilojoule, we were ultimately limited by the same instability and implosion symmetry as those designs used the same Hohlraum. And we did, however, during these experiments, learn a great deal about in-flight Ridgmeier-Meshkov and Rayleigh-Taylor instability growth that was used to improve our hydrodynamic modeling. Now, in 2016, we made a big change. We switched to first a lower density gas-filled Hohlraum, and second to diamond capsules to increase the compressibility. And this was a totally new regime for us, and that meant we had to learn all over again how to control implosions in this new design. And by 2017, this eventually paid dividends by increasing the yield to 10 to the 16 neutrons or 55 kilojoule. Target gain was still only 3%, however, and attempts to increase the convergence were unsuccessful. So we explored larger capsules that would couple more energy to the fuel. But the problem is, with fixed laser energy, simply scaling everything up would lead to less drive, and the capsule velocity would decrease and coast for longer at the end of the pulse. The coast time is the time between the laser switching off and peak compression. And that longer coast time potentially decompresses the fuel and transfers less energy to the hotspot. Now, we reduced this effect by using a capsule with a proportionally thinner radius, effectively reducing the payload of our rocket. But the problem with that was that, first of all, we still saw an increase in coast time that led to a reduction in pressure, but we also noticed that these capsules had more imperfections, and which were leading to a lot of shell material mixing into the hotspot. The good thing that came out of that was it led to a concentrated effort to make better capsules. Okay, then in the fall of 2020, to reduce the coast time from 1.5 to 1 nanosecond, we used slightly smaller capsules that were also of higher quality and achieved 170 kilojoules of fusion yield, putting us into the burning plasma regime for the first time. Then, after that, we started a set of experiments specifically designed to reduce losses, including a reduction in the size of the laser entrance hole, basically increasing the energy coupled to the capsule, which bore fruit in August 2021, delivering 1.35 megajoule. However, attempts to repeat this shot showed quite some variability in performance, and that suggested that a more robust tolerance of the target defects was required, and this led again to a modified target design, which combined with an increased laser energy from 1.9 to 2.05 megajoule got us to the fusion ignition result on December 5th. Okay, so that was a quick overview. Now I'll focus on the recent progress we made in the last year and a half that got us here. So how did we overcome the performance variability after the 1.35 megajoule result in August? So just to put everything into the landscape in perspective, let me show you this plot here, which is a plot of the hotspot ion temperature versus hotspot areal density, which is a convenient parameter space for quantifying target performance related to the Lawson criterion of a burning plasma. And you can read more about that at these references here. So these are the shot names here in year, month, day format. And so N21088 is the 1.35 megajoule shot on August 8, 2021. And the attempted repeats of this shot, the other red stars, delivered only about 250 to 700 kilojoule. So they were clearly in the burning plasma regime driven by alpha particles and the self-heating regime where alpha particle heating is dominant. Now, to understand the lower performance of these attempted repeats, we need to step back and take a closer look at the target details and the shot data. So ICF targets require state-of-the-art microfabrication precision. Here on the left, you see a picture of one of the gold-lined uranium hohlraums with the two silicon cooling arms and some cables for temperature sensors that are spread around the hohlraum. On the left is the jacket of the fill tube that we use to fill our capsules with DT fuel, and the capsule sits inside here. On the right is an X-ray radiograph of the cool diamond capsule inside the hohlraum. Now, the capsule is about 2 millimeters in diameter with an 80 micrometer thick wall, and the deuterium-tritium gas is condensed under pressure over several days to form a DT ice layer on the inside surface. There's also a thin tungsten-doped layer in the capsule wall that protects the DT ice from preheat during the early part of the laser drive, which would otherwise reduce compressibility. Now, capsule production is a multi-step process that takes almost 3 months. So we start with the plasma chemical vapor deposition onto a silicon sphere. The capsule is then polished in a V-groove on a diamond grinding disc. Then another diamond layer is grown, this time with tungsten dopant. It's again polished, and another layer is grown. And then a hole is drilled through the wall of the capsule using a laser for the fill tube, and then the silicon sphere is dissolved away using a wet etch process. Removing the silicon actually takes several days, as it uses the same hole that is used to attach the fill tube, which is only 2 micrometers in diameter. So when you look at these targets blown up on an engineering drawing, it looks so easy, but they really are a work of art. Now for the shot data. A unique set of diagnostics is applied to each experiment to improve our understanding of the implosions. First, we have Dante, which is a time-resolved soft X-ray spectrometer that allows us to measure the hohlraum radiation flux. Then we have hotspot X-ray imaging and spectroscopy, which gives us a measure of the hotspot shape and size. And we are fielding this diagnostic from multiple lines of sites. That allows us to perform tomographic reconstructions of the plasma emission distribution. And we're also doing this at multiple X-ray energies which gives us an inference of the three-dimensional electron temperature distribution of the plasma. Similarly, we also measure the hotspot and fuel shape by neutron imaging. Again, this is being done from multiple lines of sight and allows us to do tomographic reconstructions of the neutron emission spectrum. And we can combine these 3D reconstructions with the X-ray 3D reconstructions to infer things like the three-dimensional density of our plasma and three-dimensional pressure distribution. We measure the neutron yield with nuclear activation detectors. We measure the X-ray bang time and burn width with X-ray streak cameras. We measure the gamma reaction history by time resolving the Cherenkov coefficient in a CO2 gas cell that's located outside the chamber. And finally, we measure the hotspot ion temperature and velocity and fuel density using neutron time of flight detectors. And combining these neutron time of flight detectors with the nuclear activation detectors that are spread around the target chamber also gives us a yield map and fuel uniformity measurement. Okay, so armed with these diagnostics, back to the question. Why did we see so much variability in fusion yield when trying to repeat the 1.35 megajoule shot that was close to igniting? Well, we identified 3 main sources of variability. And so let me walk you through this. So here is an X-ray image of the original shot at stagnation and one of the repeat shots that produced only 400 kilojoule. The repeat shots, what was clearly driven more on the waist, so it didn't converge symmetrically. That's a first energy sink. In addition, you see these localized bright emission features here. These are a result of capsule shell material jetting into the hotspot and basically causing there a localized energy sink. The third degradation mechanism that you can't see here, but from the Doppler shift of the neutron spectrum, which is measured by the time of light from multiple directions, we observed a drift velocity of the core of about 130 kilometers per second. And again, just to put this into perspective, if you remember at the beginning, I was telling you the peak velocity of the capsule is about 400 kilometers per second. So 100 kilometers per second drift velocity of our entire hotspot as a significant fraction of that, and therefore a significant energy sink. Oh, fast. Okay. Yeah, and the other repeat experiments showed these features also to varying degrees. Now, we attribute these observations to capsule asymmetry, drive asymmetry, and capsule defect. So let's briefly walk through each of them. So first, we mode 1 drift sources, which are due to capsule thickness and centering variations, as well as the laser delivery and diagnostic windows, which are mounted on the side of the Hohlraum. Then we have mode 2 asymmetry sources, which are due to variation in laser delivery along the inner versus the outer beams, and how those beams interact with the gold bubble that is emerging when the beams hit the inside of the Hohlraum wall. And finally, we have mixed sources due to capsule defects like the fill tube, voids, pits, particulates, and high Z inclusions in our capsule. And I'm going to talk a little bit about this in a little bit. So we quantified the impact of these 3 mechanisms on fusion yields through post-shot modeling based on the measured data. So first we have degradation due to mode 1 drift, we have degradation due to mode 2 shape, and we have degradation due to hotspot mix. Now, we ran a set of simulations of the repeat shots varying these three parameters. Here, the blue, peach, and green bars are the simulated impact of each degradation mechanism for 210808. And this is the equivalent impact for each of the repeat shots. So if the bar here is very low, it means it was a big impact. Now, looking at the axis on the right here, is the resulting expected yield for these experiments, and the red diamonds are the actual measured yields for each of the shots. So as you can see, the measured yields were within 25% of our post-shot expectation over a 5 times variation, which suggests that these are the main sources of variability. And mix was determined to be the dominant yield degradation mechanism for the 1.35 megajoule repeat shots. With these capsule qualities, with the capsule quality that we got, the repeat shots we should have only expected about 500 plus minus 200 kilojoule, which is roughly what we got. So let's talk a little bit about where this mix is coming from. Microscopic capsule imperfections amplified by hydrodynamic instabilities are the dominant degradation mechanism due to mix. And on the left, I'm showing you here a capsule cross-section, which has a large pit and a large void, and some smaller size pits and voids and inclusions. And we believe that these large pits and voids, as well as the fill tube, can cause these localized mixed jets that you saw in the X-ray image earlier on one of the repeat experiments. But we also observe what we call diffuse mix, or mix that's more spread out through the periphery of the hotspot. And we know that this is mixed because we see in our X-ray images enhanced X-ray emission. There's more X-ray emission than there would be if the X-ray emission would just come from DT. And we believe that this diffuse mix is caused by some of the smaller sized pits, voids, and inclusions that are basically more distributed. Now, here in the middle, I'm showing you some of the examples. So this is an SEM image of some of the surface pits, and here are X-ray radiographs of some of the voids. And as you can see on the right, the target from the 1.35 megajoule shot had almost no defects at all. And we are actually still struggling to date to produce targets that are as good as this one. But again, the good thing here is this motivated another capsule and pulse shape design change to use a scheduled laser performance upgrade to drive even heavier and more stable capsules, which would be more tolerant of mix. Okay. So towards the end of 2022, the NIF laser energy output was increased from 1.9 to 2.05 megajoule after years of work to improve optics damage thresholds. And here the shape of the drive as well as crossbeam energy transfer were modified to improve the symmetry, and with a longer drive and slightly higher peak power, this capability enabled to use a thicker target to reach higher pressure with reduced coast time, leading to more energy coupled to the hotspot and making it more robust to all of the degradation modes. So basically, by having more laser energy available, we could increase the payload of our rocket and drive it to these more extreme conditions. And this basically led us directly to the ignition result on December 5th, 2022. Here at the bottom, again, you see the evolution and target gain from March 2021 to December 2022. And above here are the corresponding neutron images, where you can see that the neutron emission grows and increases in brightness as the fusion yield increases. And this is basically a sign of the burn wave starting inside of the initial hotspot and then burning out, converting the initially dense and cooler DT fuel into hotspot material that's then consumed by the fusion burn wave. And here on the right, I'm again showing you our overview plot of the hotspot ion temperature versus hotspot areal density. This time, including the 221204 ignition experiment. And I don't know, some of you might have seen it in the news. We were actually able to repeat this experiment just recently, end of July, where we basically did a straight repeat, and we actually got even more energy out, just below 4 megajoule of fusion energy output. So the question is, what comes next? Well, it's actually gonna stay very exciting, because this coming weekend, the NIF is scheduled to deliver 8% more energy compared to the December 5th shot, providing even more tolerance to mix and hopefully a further increase in yield. And but with that, we are far from done yet. Actually, the current NIF design with the modest modifications can support much higher performance. So we already performed 15 experiments on a single NIF quad. That's just 4 of the NIF laser beams, to study laser performance and optics damage at 2.6 megajoule and 500 terawatt, and a similar number of experiments were performed on shots above 600 terawatt. Now the 3 megajoule operating point you see here on the right is just relying on simulations, and it's therefore a little more uncertain. To get there, key changes would be to add 2 more laser slabs to the amplifiers and thinner harmonic converter crystals, while continuing to our work on the optics hardening. So with that, I hope I've been able to show you that NIF has not yet reached its full potential, and we plan to sustain and modernize NIF in the coming decades with the goal of reaching tens of megajoule yields. And that work and the science it enables will require significant effort from engineers, technicians, and scientists. So this is really a great time to engage for everyone in the field. Now, finally, fusion ignition also provides a fresh impetus and the scientific foundation for inertial fusion energy. IFE is the next grand challenge, and realizing the potential of IFE will require developing crucial new technologies. We believe the scale of investment will be comparable or more to the investment required to obtain ignition. And with community partnerships and in synergy with our mission, Livermore aims to enable an ecosystem to accelerate IFE in support of the Department of Energy's decadal vision for commercialization of fusion energy. All right, so with that, I'd just like to summarize. If I can get to the next slide. By saying this was an accomplishment built on decades of hard work and dedication by the community, some of which are listed here, but many more contributed to this work. And next year, assuming that our funding will increase, we will be hiring. So please visit us at careers.lnl.gov. And with that, I would like to thank you for your attention. Questions?
The talk is now open for questions. We'll take questions from people in the audience first, and then check to see if there are any questions from people in the webinar.
Could you give us any idea of the neutron flux that you produce on December 5th? And what do you expect the neutron flux would be when real ignition would be achieved? And what is the plan to deal with it?
Yeah, so real ignition was achieved, right? at least according to the National Academies of Sciences definition of ignition. But in terms of neutron flux, so we are producing about 10 to the 18 neutrons in one experiment. Neutrons go into 4 pi, so you can use that to calculate the flux at whatever distance you like.
In the ignition shot and the follow-on shot, how much fuel is actually in the pellet? If I recall, it was something on the order of 50 to 100 megajoules of potential DT fuel. Is that correct?
Yeah, so our burn-up fraction is only about 4% or so. So the majority of DT fuel did not get burned, actually, even in that experiment.
So before turning the laser up anymore, what's the path to getting a better burn up?
I mean, I guess it's an interplay between confinement time and compression. So, you know, if we are able to increase the compression and the density of the surrounding shell, you know, we basically have more time to burn up more of the fusion fuel before everything starts to explode just from PDV forces. So, you know, eventually getting to hotter temperatures in the hotspot and higher and better confinement should increase the burn-up fraction. But we would never expect 100% of the fuel to burn, in at least not in this design. Maybe I think numbers that are you know, in simulations predict that maybe we can get up to 30% burn up.
As part of NIF's future development path, will you be looking at ways to reduce the external energy input to get those 2 megajoules? I mean, you mentioned 300 megajoules of capacitor banks, et cetera, Is that one thing you're looking at?
So, yeah, as you point out, the NIF is really not designed to be a fusion power plant by any means, because the laser technology is just not very efficient. We lose a lot of energy just with those flash lamps, and we currently don't have any plans to upgrade NIF's laser technology in that direction. For example, you know, we could use diode pumped lasers, which would be much more efficient. And any inertial fusion energy concept that would want to use that approach would have to use a more modern laser technology.
A very nice presentation. Many of the NIF diagnostics rely on nuclear data processing. So do you think that there's some nuclear data which need to be improved for such a diagnostic? So
well, I mean,
activation, for example, flux measurements, etc.
Yeah, so I think it really depends what you want to measure, right? So one thing, for example, that would be really cool if we could actually time resolve our neutron flux that comes out of the implosion during the actual implosion. And so right now our neutron time of flight detectors, they are basically too far away to actually give us any time resolution. So that would be one ambitious project to improve on the nuclear diagnostic side.
Question? Do we have any online? So I do have one question. That's about the photon. And does that in any way limit the amount of laser power you can put on the pellet, or can it take an automatic power you have?
You know, that's a really good question. I don't know exactly the answer, but I could imagine that, you know, eventually the laser intensity, you know, becomes very high, and you might have a hard time actually getting that power into the Hohlraum. But I don't think we are anywhere near that at the moment. But I'm not 100% sure.
Go to more power, then you can make the whole one bigger. And there was always at the beginning designs of NIF, the desire to go to much bigger energy than 1.8 megajoules, but that was the limit that was set by the funding agencies on what could be done on NIF at the beginning. But bigger energy would be great, because you don't have to gas fill the whole room and many things advantageous.
Yeah, thanks for that perspective.
All right, let's thank both speakers of this session again.